Okay, what we're going to cover next is orthogonality. A lot of early material that we already covered in the previous lecture. So we need to review first. Okay, we're going to review first. Let's go over the inner product first. Okay, this is something I covered at the beginning of the semester. Inner product. Suppose we are given two what? Vector, u and v. They are the vector in what? Say in Rn. Okay? And what's the inner product of u dot v? Okay? It's u, we transpose it. Okay? U to un times what? V to vn. So this end up with u1 times v1 and u2 times v2 all the way down to un times vn. And then sum them up. Okay? So let's look at a very simple example. What is u dot v? U is 2 minus 5 minus 1. V is 3, 2 minus 3. So u dot v going to be 2 times 3 plus minus 5 times 2 plus minus 1 times minus 3, and now it's minus 1. Okay? This is very trivial. So we just go over. So that you recall what you learned at the beginning of the semester. Now the theorem. Let u, v, w be vectors in Rn space, and let C be a scalar. Then u times v is what? V times u. This is called what? Commutative. For the inner product between two vectors. Okay? And u plus v times w is equal to u times w plus v times w. Times here means inner product. Okay? And then cu times v is c, you do the what? Product first, u times v first, and times by the scalar. Or you can apply c to one of the vector, okay? And then u dot cv, that's also what? The same. And u dot u always greater than 0, okay? And well, this is actually what? This is actually the norm of the vector square, okay? U dot u is equal to 0 if and only if u is equal to 0. Definition: the length or norm of a vector is a non-negative scalar. We put what? Notation like this. Two what? Two vertical lines, okay, around the v. And the norm of v is square root of nu times nu is equal to what? V1 squared plus all the way up to Vn squared, okay? And the norm square is nu times nu, okay? So you can claim, see those claims, very trivial. Cv, the norm square is Cv dot Cv, which is C squared, V times V, is C squared what? The norm square, okay? And a vector whose length is 1 is called the unit vector. That's a definition, okay? The vector whose length is 1 is called the unit vector, okay? And how we get the unit vector? Well, for any given what? Vector v divided by its length, we call this normalizing what? A non-zero vector v. After you normalizing a non-vector v, you get a unit vector, okay? So in this case, uv have what? Have the same direction. UV have the same direction. The only difference is they have different lengths. One is unit length, and the other one is what? It's given original length, okay? So that is about what? Something we covered before. We go over so you have a systematic review about what we have covered so far at the beginning of the semester. Now, let's look at some example for the material we just reviewed. Let W be the subspace of R squared spanned by a vector X. Its X1 coordinates 2/3, X2 coordinate 1. And we find a unit vector Z that is a basis for what? For W, okay? If you look at the picture very quickly, this is X1, this is X2. So this vector here, so this vector here, two over three should be here. Okay, this is the vector. Okay, and the subspace spanned by what? This vector going to be the line. And the line goes through what? The origin 0, 0. Okay, goes through the origin 0, 0. So if I call this is what? X. So the line is what? Line is a span what? Span of the X. Okay, we're going to use the concept later. Okay, so you can verify any line in R2 space goes through the origin is a subspace. I think we proved that before. To simplify the calculation, let's begin with y equal to what? 2, 3. The same direction, but get rid of what? Get rid of the fractions, okay? Fraction create what? The complexity in doing calculation, okay? So let's begin with what? No fractions, but the same direction, 2, 3, okay? And the norm is 2 squared plus 3 squared, which is 4 plus 9, which is 13. Take square root. So the norm of y is square root of 13. And Z1 is what? 2, 3. And you divide it by what? By the length. Okay? By the length. So in this case, Z1 is 1 over square root 13, 2, 3. Okay? And Z2. Okay? Z2 is 1 over square root 13 minus 2 minus 3. Are both what? Unit vector. That can be a basis for what? For W. One goes this direction. That's my Z1. And Z2 goes this direction. Okay? But doesn't matter which direction it goes. Well, the vector is always on the line that goes through what? The origin. Okay? Now, let's look at the next one. For UV in Rn space, the distance between two vectors written as distance of UV is defined as follows. Distance UV, you take the norm U minus V, okay? U, the vector, minus the other vector V, okay? And you take the norm. That is the distance between what? UV, okay? That's the distance between UV. So, compute the distance between what? UV. U is 7, 1, V is 7, 2. Okay, U minus V, 7 minus 3 is 4. 1 minus 2 is what? Minus 1. And you take the norm, okay? 4 squared plus minus 1 squared, which is square root of 17. Now, look at here, definition. Two vectors U and V in Rn are called orthogonal to each other if their inner product U times V equal to 0, okay? By the definition, 0 vector is orthogonal to what? Any vector, because any vector times 0 will eventually equal to 0, okay? I think we covered this before. And theorem, Pythagorean theorem, okay? two vector UV are orthogonal if what? If the norm of U plus V square equal to norm of what? U square plus norm V square. Okay, this is called Pythagorean. See, we covered that as well. Just quickly review the concept that we covered before. Okay. This is something we did not introduce you at the beginning of the semester. Okay, this is called orthogonal complements. Let's take a close look about those definitions. Definition: a vector Z is orthogonal to every vector in a subspace W of Rn. Then Z is said to be orthogonal to W. Okay, let me try one more time. If a vector Z is orthogonal to every vector in the subspace what? W of Rn, then Z is said to be what? Orthogonal to W. And you look at the picture here. Okay? Suppose the Z is this what? Z-axis. And W is formed by what? Formed by 1, 0, 0 and 0, 1, 0. So that is what? W is the xy plane. Okay? So this vector Z is perpendicular to each what? Each vector in WY plane. Okay? So this is the situation you can imagine. If set of all vectors Z that are orthogonal to W is called the orthogonal complement of W. Okay? Orthogonal, the orthogonal what? The set of all vectors Z that are orthogonal to what? W. Remember in our example here, think about the W is what? The W can imagine that W is what? Spanned by E1 and E2, right? So this is XY plane. And any vector that is perpendicular, no, not perpendicular, every vector that is parallel to 0, 0, 1 will be what? Automatically orthogonal to the plane. Okay? So the set of all vectors Z that are orthogonal to W is called the orthogonal complement of W. Okay? And it's denoted by what? W, we put what? Something like this. Okay, something like this. And how you read this? This is called W perpendicular. That's the way how you read the notation. Okay? So this is the one I just mentioned. You can imagine that the span E1, E2 in the space is what? The XY plane, which form what? A subspace in R3. And the Z vector, say this is 0, 0, 1. That's E3. Okay? E3 is perpendicular to XY plane. And any three-dimension what? Vector, which is parallel to E3, they will form what? The orthogonal complement of W. Okay? So imagine that W to be the XY plane and let L be the line through the origin. Okay? Perpendicular to W. And you can say, as I mentioned earlier, L is what? The Z-axis. Okay? So in this case, we can say L is what? L is W what? Complement. W what? Perpendicular, not complement. Okay, L is what? W perpendicular. And W is what? L perpendicular. Okay. And properties about what? W perpendicular. A vector X in W perpendicular. A vector X is in W perpendicular. X is what? Orthogonal to every vector in a set that span what? Span W. And two, W perpendicular is a subspace of what? Rn. Okay, that's quite trivial. Now we're going to invite for what? We're going to Now the known fact, we know what? We know the column space of a given matrix A. How you determine it? Well, it's just what? The column matrix A, the transpose, and you find its low space. Okay? Let me explain what does that mean. Suppose this is my given what? Matrix. So this is my given matrix. Okay? So this the matrix is what? Is 2 by 3. Okay, it's 2 by 3. So when this is 2 by 3, you know what's a column A, right? By definition, column A is what? Column space A, which is spanned by what? Spanned by column of A matrix. Okay, column of, so this is my A1, this is my A2, this is my A3. But you can also what? This is equivalent to what? It's equivalent the same space spanned by your E1 and E2. What's E1? E1 is 1, 0. E2 is what? Huh? 0, 1. Both span the same space, R squared. Okay, this is actually equal to R squared. But this is better in the sense that E1 and E2 are linearly what? Independent. Okay, so you can use just this two. Okay, so this E1, E2 is the basis, but A1, A2, A3 is not basis because A3 can be written as a linear combination of A1 and A2. Okay, so in this case, what is the rank of A? Rank of A is a dimension of what? Dimension of what? Column space of A, and that is 2. Okay, this is something we covered before. Just review. Okay, now look at what's A transpose. A transpose in this case is 1, 3, 3, and 2, 4, 3. That's A transpose. Okay, so the column space of A transpose, okay, is actually equal to what? This is the original row. Okay, so it's actually what? The row space of what? A. Okay, that's how they're related to each other. So when somebody asks you to find what? The row space of A is very easy. You just make a transpose, make it an A transpose, look like this, and use the way we introduced you before to find out the column space of A transpose. Okay? So if A is an n by n matrix, n row, n column matrix, then the orthogonal complement of the row space of A is the null space of A. Okay? And the orthogonal complement of the column space of A is what? The null space of A. And look at the picture. This is what? Say this is the row space of a matrix A. And perpendicular to what? The null space of A. We will give you the proof, okay? And the current space of A, the complement, the what? The perpendicular what? Huh? Space will be null of A transpose. We give you a proof, okay? And this is a fundamental subspace of an n by n matrix, okay? So it's very easy for you to remember, okay? If this is null A, if this is row A, row space of A, and this is what? Current space of A. The one perpendicular to what? Row space. Going to be what? The null space of A. And the one perpendicular to what? Current space of A going to be null of what? Huh? A transpose. Okay, they both come with null, but this is A itself. This is what? You need to make a transpose. We will give you a proof, okay? Just memorize the lines now. Now, recall the current space of the definition, the current space of n by n matrix A, denoted by current space of A, is a set of all linear combination of the current of A. Okay, so if A matrix can be written as what? In what? In columns. Okay, each one, A1 is in Rn. A2 is also in Rn. Okay, all the way up to An is in Rn. But how many of them in column? So that's why this is what? M by N. Okay? So column space of A is spanned by A1, A2 up to An. And what is the meaning? What is the meaning of the column space spanned by A1 to An? Is A times X for any what? X in Rn space. Okay? If they multiply, can give you what? The B. And you make the correction on those B. So formed by linear combination. Okay, formed by the linear combination of A1 to A. And look at here, related theorem 1. The current space of an n by n matrix is a subspace of Rm. Okay? And the current space of an n by n matrix A, they are all in what? Rm. So the equation Ax equal to B has a solution for each B in Rn. Okay? So let's take a overall review again. If I say Ax equal to B, okay, A can be written as A1 up to An. N is Nancy, okay? And particularly, you can imagine N equal to 4, okay? N equal to 4. You have 1, 2, 3, 4, 4 column. And M is what? 1, 2, 3, 3 rows. Times X is X1, X2, X3, X4. So this times this give me B1. This times this give me B2. This times this give me B3. And B1, B2, B3 is in R3. And that's my M as mother. Okay? So look at here. Column A is span of A1 up to An. Okay? So you make a correction for A, for what? For all B. That B equal to what? Ax, huh? Ax times X equal to B. You correct all such B. And here X is in what? In Rn. Look at here. Rn, N is 4. Okay? So that's way how you understand it. Let's look at some question. Okay? I think there's a question in the sample exam. You know what? Before we go to the sample exam, we may want to take a look about this first. Okay. Look at the question here. The contrast between what? The null space A and column space of A. Okay. This is a review about what we covered before. Now, if A matrix is what? 2 minus 2, 3, that's your A1 column. And this is A2 column. This is the third column of matrix A, the fourth column. Okay. Now, if the column space of A is a subset of Rk, what is K? Well, this is related to what I just covered, right? The column space. Okay, the column space. You have 1, 2, say you have four different columns. 1, 2, 3, 4. So n is 4. But row is 1, 2, 3 row. Okay? So AX times B is what? Is 1, 2, 3. Okay? B1, B2, B3 is in R3. Okay, it's in R3. And what is your column A? Column A is span of A1, A2 to what? AN. N is 4. And you correct all the B such that AX equal to B. But what is B? B is 1, 2, 3. So it's M. Okay, it's M. M is 3. So keep that in mind. You can look at here. Okay, look at here. This one, okay, is going to be equal to what? Some B, right? This is a extension of what we covered earlier. Okay. Okay, look at here. The column space of A is a subset of what? Rk. What is K? Look at here. The column space is spanned by what? A1, A2, A3, A4. So it's C1, A1, C2, A2, C3, A3, C4, A4. Each column what? Vector is in R3 by the linear combination of C1, C2, C3, C4. They are numbers. By this linear combination, the vector end up with in what? In R3, which is M. M is what? Huh? M is the number of rows of the matrix A. So a subset of Rk, what's Rk? K is Rm. M in this case is 3, so K is 3. The column of A, each one has 3 entries. So the column A is a subset of Rk. K is 3, okay? Now, let's look at what? The null space. What's a null space? Null space has a different definition, okay? You look at the homogeneous what? Linear system. AX equal to 0. This is 0, okay? This is 0. And we've tried to correct what? The X. We try to correct the X such that A times X equal to 0, okay? A times X equal to 0. So you look at the system. It correct the X and X from the space. And X, in order to be multiplied, compatible to matrix A, X need to be X1, X2, X3, X4. It need to match what? The column number of matrix what? Matrix A. Look at the system, okay? Augmented A, as I mentioned in this example, okay? 2 minus 2, 3. 4 minus 5, 7. Minus 2, 7, minus 8, 1, 3, 6. Okay? It has 1, 2, 3, 4, 4 column. In order to make multiplication work, is this times this need to be equal to what? Here is replaced by what? 0, 0, 0. That's for null space. Okay, you try to correct what? All those x. Okay? This times this equal to 0, 0, 0. This times this, no. This times this equal to this 0. This times this equal to this 0. This times this equal to 0. In order to make what? The computation what? Meaningful. This must be x1, x2, x3, x4. So this is a subspace in what? If you correct such x, okay, they are the vector in R4, okay? So look at here, the notation. Null A, I correct all x. A times x equal to 0. I correct what? All such x in R4. So the null space is a subset of RKK is equal to 4, okay? Okay, I'm recording now. So let's look at for the question and its description. This is the sample test. If the null space of a 50 by 60, okay, this is my n, this is my row, and this is my column. You have 50 rows and 60 column. Matrix A is what? 40 dimension, okay, the null space. And we know by the rank 0. By rank 0. By the rank 0, we know rank of A plus dimension of the null space of A. They should add up to what? They should add up to the number of what? Of columns of matrix A. So in this case, the number of columns for the matrix is 60. And we say dimension of the null space is what? Is 40. So the rank A must be what? Must be 20. Okay? So you can figure out rank of A is 20. That answers the first question. Okay? Rank of A is 20. Now, null space A is a subspace of Rn. What is N? The subspace of Rn, right? So look at here. I use the same example. This is A1. Huh? A11, A21, A31, A what? 12, A22, A32, A13, A23, A33, and this is A14, A24, A34. Okay, so the column, this is A. Suppose this is A. You can write it as what? As A1, A2, A3. Oh, this is separate. Okay, nothing to do with the example. This is A4. Okay, so look at here. The linear combination of A1, A2, A3, A4. Each one is what? Huh? Each one is a vector in what? Each one is a vector in, huh? In R3. In R3. Okay, it's not in R4, R3. So that is what? How many entries in column of A? Okay, so how many entries in column of A? No. Let's see. How many entry in column of A? You have 1, 2, 3. That's actually what? The row number. Am I correct? Look at here. Each column vector in matrix A, number of entries is equal to what? The row number, right? So row number here is what? Row number here is, let's say I need to be a little bit careful here, okay?